gustaría invitar a John Hess, que viene de California, viene de la organización de CINIC, que es algo similar a CUDI. Y bueno, pues nos va a platicar un poco sobre lo que hacen y obviamente la presentación va a ser en inglés. En las preguntas, una vez que ya abra las preguntas, si necesitan que lo traduzca, solamente hagan la pregunta un poco despacio para poder tener oportunidad de traducirla lo mejor posible. No soy traductor, pero sí lo puedo hacer. O la pueden hacer en inglés también, obviamente.
Buenas tardes a todos. Thank you for the introduction. And I apologize that I'll be giving my talk in English. So bear with me and we'll handle questions as they come. So thank you once again. I'm John Hess from CINIC and very happy to be with you here today. So I'm here to talk to you about the Pacific Research Platform, something that Carlos had seen Larry Smarr speak in Washington, D.C. and earlier in the year at the CINIC conference. And as I mentioned, I'm with CINIC. CINIC has a long history of working with CUDI. I think it was in 2000 that CUDI connected into the San Diego supercomputing facility. Carlos, I think, was there working with Tom West of CINIC and Governor Gray Davis and President Ponce de Leon of Mexico. And we hope to continue that collaboration as we move forward with this Pacific Research Platform. So I just, for a level set, most of you are familiar with CINIC. So that CINIC provides research and education connectivity within California to the public school systems, the University of California system, Stanford, Caltech, University of Southern California, as well as the California State Public Library System. So there are about 11,000 institutions in California that use CINIC, and about 20 million people in California use CINIC every day. Pacific Wave is an organization collaboration between CINIC and the Pacific Northwest Gigapop in Washington State, and we provide kind of the backplane with CINIC for the Pacific Research Platform. So what is the Pacific Research Platform? So what we're increasingly seeing is that research today is multi-investigator, multi-institutional, and depends on a ever more rapid access to large data sets. And these data sets are distributed across large geographic distances. So in 2015, a group created this Pacific Research Platform. It's an NS-funded project to meet the needs of researchers in California, the Western US, and beyond. So the PRP is working to accelerate discovery by improving end-to-end data transfer, data placement storage, and computing capabilities in collaborative big data science, and by facilitating direct engagements between campus technical engineers and multi-campus science teams to inform and drive the requirements for the network. The scope of the PRP covers a broad range of data-intensive science, including projects from the fields of particle physics, astronomy, biomedical sciences, earth sciences, and computer science and engineering. The PRP is a partnership of more than 20 institutions, including 4 national supercomputing centers. So as I mentioned, we're in the earlier panel about the supercomputing centers and connecting into the San Diego Supercomputing Center. Among the other supercomputing centers, part of the Pacific Research Platform is the NASA Ames Supercomputing Center in Northern California, the NERSC as part of the Department of Energy's Lawrence Berkeley Lab in Berkeley, California, as well as NCSA, National Center for Supercomputing Applications in Chicago. So the PRP is led by scientists. Larry Smarr is the principal investigator out of Cal IT2 in UC San Diego, as well as Camille Crittenden as a co-PI out of Citrus. Cal IT2 and Citrus are two of the 4 Gray Davis Institutes of Science and Innovation created in California to accelerate science. And among the other co-PIs are Tom DeFonte from Cal IT2, Phil Papadopoulos from UCSD and SDSC, and Frank Werthwein from UCSD Physics and San Diego Supercomputing Facility. So the PRP is focused around several science teams in a broad range of scientific domains. Among them are visualization and virtual reality, biomedical, earth sciences, as I mentioned earlier, particle physics, astronomy and astrophysics, and some new ones that have come on since we started the project, and that includes cryo-EM, deep learning and robotics, and high-performance wireless. So what I'd like to talk to you about today is how the PRP version 1 took the ESNet science DMZ model to scale it to a regional model. I want to also talk about science engagement. This is kind of a socio-technical engineering among the contributors from the science and teams, network, and HPC staff. Some examples of the science drivers from those scientific domains, and what we envision for the next version of the PRP version 2, as a testbed for incorporating security, IPv6, SDN, SDX, and cooperating research groups. And among the considerations as we look ahead of scaling the PRP from a regional model to a national and international models. So as I mentioned, the PRP took the ESNet developed Science D model and extended it to a regional scale. So the Science DMZ was designed to address data movement among researchers at the Department of Energy National Labs. And the idea is that this is a friction-free network path, that you're using highly capable network devices that are wire speed, have deep buffers, deep queues, that virtual circuit connectivity is an option, and that the security policy is not impeding the science workflows. And that this is typically something that the DMZ is located at or near the campus perimeter or border. Another component is dedicated devices that are called data transfer nodes. We'll talk about these in terms of the PRP. We also use the acronym FIONA for a flash I/O network appliance as DTNs. So these DTNs are focused for data transfer. So they typically don't run web servers or mail servers. They're focused on high-speed transfers across a wide area network. And so the idea is that these form kind of capacitors in data movement, and that they cooperate with data movement toolsets such as Globus and GridFTP, among others. Another important component of the Science DMZ is measurement. And they have, typically you'll have a dedicated device acting as a measurement node or running per-sonar software or other measurement software. And another critical component in the Science DMZ, again, here at the bottom, is the engagement, the science engagement with the end users. This is where you're reaching out to the researchers, discussing with them their science workflows and how we can make a positive impact. So in 2014, we met in Stanford with Larry Smarr, other regionals within California, ESNet, and what we determined is, can we build a prototype of regional scale out of a bunch of independently managed networks? So the challenge was take the campus DMZs that were funded by the NSF, regionals such as Scenic, and nationals such as Internet2, and international partners such as the Glyph, and how can they work together to produce predictable performance? So what our initial goal was focus on disk-to-disk data movement from the eyes of domain scientists. For the scientists that are collaborating with peers across either regional scale or international boundaries, the movement of their data is their only real metric of concern. We're not asking the researchers to be network engineers. That's the job of folks like me. So out of an earlier effort, as we were discussing the Optoputer at UC San Diego and among the supercomputers at UC San Diego Supercomputer Comet among them, Phil Papadopoulos and Tom DeFonte developed a device they called a FIONA, Flash I/O Network Appliances. And these were to act in the role of a data transfer node. So in this case, the problem that they were trying to solve was how can they move data at speeds that approach 10 gig, 40 gig, and even 100 gig connected networks. So at a lower cost. So at the lower portion of the slide, you can see that they have developed platforms that provide 10 gig and 40 gig connectivity for around 8,000 US. And 100 gig DTNs are in the neighborhood of 15,000 US, depending on how they're configured. So to address even the lower speed connected networks at lower cost, we took an off-the-shelf, kind of a home theater PC platform that it has a 1 gigabit connection and can be configured with 2 terabytes of flash for around $1,000. And so this is part of the, I guess, the spectrum of FIONAs that we've developed. And the FIONAs themselves, besides DTNs, they can also be purposed to act as dedicated perf-sonar nodes. We're also exploring low-cost perf-sonar nodes. This particular is a single board computer or development board that you might see folks using for developing either tablets or smartphones. This is an Odroid C2 and has a 1 gigabit connection. And when configured with about 32 gigs of storage, it's around $100 US delivered. And this is an ARM-based computer. We're looking at this not only within the scope of the Pacific Research Platform, but within Scenic, we're looking at these devices to help us instrument our school districts and our community colleges that are part of the community with which we serve. So over the scope of the project, the Pacific Research Platform, we've produced about 30 FIONAs that have been deployed to participating campuses and institutions. And so this includes, as I mentioned, the data transfer nodes, the perf-sonar nodes, as well as larger DTNs that have a lot of storage within the skin of the device, so up to 160 terabytes of spinning disks, as well as the faster, newer technology, NVMe, that's about 10 times faster than standard flash SSD. We're also looking at compute transfer nodes. This is where we're taking 10 up to 12, between 12 and 48 standard cores within dual processor units, but also adding in GPUs that are for the commodity gaming market. So this is the idea to address where researchers are looking for CPU core hours, where they might turn either to a supercomputing facility and perhaps have a challenge getting time on those, or turning to like the spot market that Amazon, for instance, offers for compute. In this case, we can deliver up to 500,000 GPU core hours per day. So the other application that the GTNs, the FIONAs, have been put to are virtualization transfer nodes, where we are looking at between 3 and 45 panels tiled together that can deliver up to 180 megapixels in 2D and 3D. So one of the ways we've talked if we went back to that science DMZ slide, that measurement is an important component. So ESNet and Internet 2, as part of developing Personar, also has developed a dashboard. So what we're looking at is what they call a MAD dash, or a measurement and debugging dashboard, where we have taken an ESNet contributed Python script to parse the grid FTP transfer logs and upload the data results as throughput into a measurement archive, and then visualized on this MAD dash. So what we're seeing is a grid of all computers in the row communicating, testing to all the computers across the columns. So what they're moving is a 10 gigabyte reference data set that ESNet provides. And what we're measuring then is the wall clock for moving that 10 gigabit file from one disk to another between these hosts. So in this case, green is good. So those cells that are green are indicating a disk-to-disk throughput above or equal to or above 5 gigabits a second. And orange indicates that either that we were not able to retrieve the data for those transfers, or the transfers aren't happening. So what we'll show here in the next animation is the progress over the 1.5 years that we've gone from 12 sites to participating in this grid FTP testing to 24. And also the benefit of the MAD dash is finding the issues that are preventing the high-speed data transfer. So you'll see less orange and more green in the second larger grid. So in terms of scaling, as you saw that kind of larger grid, when you start talking about an N by N grid, it quickly becomes untenable to have a full mesh testing. So what we're moving toward is the concept of cooperating research groups, where researchers within a given domain that have an existing collaboration, we're trying to represent them in a smaller grouping of testing, so that in this case, this grid is showing testing among climate scientists. And again, if you can read on the right-hand side of the slide, this includes hosts at University of Illinois at Chicago, San Diego, University of Hawaii, UC Irvine, University of Southern California, the National Center for Atmospheric Research in Colorado, as well as one of our California state colleges, San Diego State University. So among the other things that we're talking about in the PRP is there's the technical side, where we're trying to understand how we can move bits faster. The other part of this is science engagement. And so this is where we're looking for existing collaborations among peers, researchers at different institutions that are trying to work together, and maybe that because they're acquiring their data in one location and need to get to a supercomputing facility at another location, that they're either shipping disks via FedEx or perhaps putting them in a car, taking them on an airplane and delivering them. Where we're trying to meet them is through a series of workshops to understand what their challenges are and how we can assist them in improving their science workflow. So in this case, we've held a series of workshops within California based on different science domains, going from the Atlas project of the Large Hadron Collider to astrophysics and astronomy, as well as visualization and cultural heritage, as well as in addition to biomedical genomics. So again, part of the science engagement that we've been focusing in the different domains that were included in the scope of the PRP include the particle physics, the biomedical omics, earthquake engineering, telescope surveys, as well as the visualization. So this is one of the examples here that Xiaofeng Dong at University Santa Cruz, as a recent hire as a cyber infrastructure engineer, is working together to connect a 100 gigabit connected FIONA at UCSC with the UCSC Hades cluster to the supercomputer facility at NERSC at LBL. And what they're processing here is 250 images per night for a storage impact of around 800 gigabits per night. So another, again in Northern California, at UC Berkeley, there's the Pacific Earthquake Engineering Research Center. This is includes labs at UC Berkeley, Caltech, Stanford, UC Davis, UC San Diego, and UC Los Angeles. And in the lower left corner, you see the Cal IT2 engineer John Graham installing the $1,000 US FIONA net at the shake table at the Pier facility at UC Berkeley. And so this is an example of distributed virtual reality. So this is taking, in the left-hand side, you see a wave installation at UC San Diego at Cal IT2, transferring images to a wave installation at UC Merced in the Central California. So this now can take each image is about 2 gigabytes, transfers in about 2 seconds between those two locations, so around 8 gigabits a second. So as I mentioned earlier, the prototype of the PRP has attracted new application drivers. So one of them is Jupyter, or Jupyter Hub. So this is a development of the IPython project. So we have FIONAs out of UC Berkeley and UC San Diego. And the Jupyter Hub, if you haven't heard of it, is wonderful for the pedagogical instruction. It's kind of the digital notebook that students will be using as they go through their courses, where you can have your code and your data and your processing all in one notebook. It's very cool. Cryo-EM, again, this is taking the scanning microscopes and making movies, taking out of captures that are happening about once every 60 seconds and producing large data sets that can be played back over time. We talked about the high-speed wireless research and education network, or HPREN. This is, in one of the earlier talks, we talked about the Scripps School of Oceanography out of UCSD. Frank Vernon from Scripps, this is using HPREN for taking mountaintops locations in Southern California instrumented with cameras to help in looking at California's wildfires. Even though we had quite a good rainy season this past winter, we're still under drought conditions, and wildfires are very much of a concern. So we're looking to extend the HPREN for other uses. I think one of the other talks was the challenges of getting imagery out of the telescopes down to where they can be processed. So in this case, HPREN is used for the Palomar Observatory to deliver images to Caltech to where they're processed. We also have, as another example of a new science driver in cultural heritage, Tom Levy, where he's taking 3D imagery from archaeological expeditions and then representing them in data sets that can be viewed remotely and through 3D immersion. And then again, another is climate science, Scott Sellers and Marty Raff, and for the Center for Western Weather and Water Extremes, mapping data sets as they collaborate with their colleagues at remote locations. So what do we look for as we move ahead into the next version or next iteration of the Pacific Research Platform? So among the challenges that we've encountered with the first iteration is at a technical level, selectively announcing reachability of science DMZ resources, choosing a traffic engineered path, and implementing tools that ensure traffic fits within the security models among the participants. So we're in the process of deploying a BGP pilot to explore those solutions using PRP. So what we have done at Scenic is that Scenic has a kind of stratified model of networking. We have a network for commodity internet access, a dedicated network for high performance research, and the PRP is adding another abstraction layer by deploying this, we're exploring by deploying this pilot using a new autonomous system number assigned from Aaron. So how that's going to look is that we're in the process of deploying route servers at Pacific Wave exchange points that will perform a control plane for announcing reachability of the science DMZ resources while using the high-speed layer 2 data plane for the actual data movement. So we'll be using reserved BGP communities for tagging routes associated with science DMZ networks so that those can be used as hooks for doing traffic engineering with BGP. And then among the things that we're trying to advocate for in the PRP version 2 is the adoption of IPv6. So we put a stake in the ground that the pilot will be IPv6 only, but we may support v4 as a transport. So the initial phase of this pilot will include UC San Diego Supercomputing Facility, UC Santa Cruz, Stanford, NCSA in Chicago, as well as the University of Illinois at Chicago EVL lab. So among the things that we're going to be looking at stretch goals for this pilot is taking BGP, adding SDN SDX for dynamically provisioning super channels supporting data movement among the cooperating research groups. And so this is probably an eye chart for those in the back of the room. So this is just a high-level topology diagram laying out most of the Pacific Wave resources in Seattle, Sunnyvale, and Los Angeles, some of the scenic components that form the core, and the participating sites. So all the sites represented here are PRP partners. The light blue are going to be the locations that are participating in the pilot, and the gray locations are where we have deployed these FIONAs as DTNs. And so as you can see that we have connectivity within California, the Western region, as well as some international partners in Korea, Japan, Sydney, and Australia, as well as in Amsterdam. So this is just a little bit more detail about the pilot itself. So as again, zooming in just on a couple example sites, showing the route servers at the 3 Pacific Wave locations. So the route servers are running either Quagga, which is an open source BGP daemon, as well as routing daemon. We're also using Juniper's VMX product, which again is a virtual router that can run on either VMware or KVM hypervisors. And so again, this is forming the control plane to which the participating institutions would form eBGP sessions to announce reachability of their science DMZ routes, but the actual data plane path will be switched over layer 2 connections through Scenic's CalREN HPR, as well as Pacific Wave's layer 2 infrastructure. So as I mentioned, part of the stretch goals that we're looking at in this pilot are dynamic circuit services. So initially, this is going to be the initial cut at that will be using NSI signaling. So this is one of the projects of GLIF, the Global Lambda Interchange Facility, where we're using NSI orchestrated services traversing, in this case, on the previous slide, the Seattle, Sunnyvale, and Los Angeles POPs. And in this case, during our initial implementation, each of the Pacific Wave exchanges operates as its own exchange. And we're using as part of the signaling control plane infrastructure, the Open NSA, which was developed by Nordernet. And for provisioning, we're using a RMP-developed MACAN web user interface. And so this is sort of again, high-level topology of the resources that we're making available through NSI. So here we have, in Pacific Wave, we have 10 gig and 100 gig, 10 gig and 100 gig connected perf sonar nodes, as well as a PRP contributed 100 gig connected DTN. And again, just kind of the abstraction of the MACAN UI, the NSI control plane, OpenNSA is the interface between the NSI, the North Bridge, South Bridge down to the layer 2 devices. And this is just a quick look at, just a quick look at the MACAN unit interface. It has a very nice high-level topology diagram of the circuit that you're provisioning. In this case, we're provisioning a circuit from Los Angeles to the Netherlands. And this is something that early in the PRP, we were trying to provision a VLAN from UC San Diego to the University of Amsterdam involving 7 administrative domains. This is something that took us months when we were exchanging probably, I think, about 40 different emails in the chain to work out that provisioning. Using this tool and NSI, this can be provisioned in a matter of minutes. So this is very cool. So what we're looking for is that in the next phase of the pilot, that we'll be using SDN and SDX to further reduce that time so that it is based on flows passing through the traffic to provision the data plane path dynamically. So this graphic gives a sense of the connectivity for Scenic and Pacific Wave, including our connection with CUDI out of the Southern California. So in this case, this is something that the PRP is using the Pacific Wave and Scenic, again, as the backplane to reach not only the research universities within California, but the Western region and the US national footprint as well as international partners. So, as I mentioned earlier, we had among the significant contributors to the partnership with the Pacific Research Platform has been the Department of Energy's Energy Sciences Network, or ESNet. And Greg Bell was the director up until a short time ago. This is one of the quotes that I like from our meeting back in November of 2014, is that just to read the quote, "For the hardest problems, not just in physics, but in climate science and genomics, there are massive teams working around the world. Our job is to make geography relevant." And so as a network engineer working for Scenic and Pacific Wave, that I take that very much to heart, is that my job is to help our researchers collaborate, and that they shouldn't have to be network engineers to do that. They should be able to do their science. And so that's something that, in talking with Carlos, that we would like to help and participate and collaborate with CUDI and the universities within Mexico so that your researchers and our researchers are not fighting geography or borders or walls to move data and to collaborate. So here are some of the resources that we use within Pacific Research Platform, and that is it for my talk. Thank you. Muchas gracias.
This is Asael Fernandez, National Autonomous University of Mexico. You mentioned that you are considering native IPv6 support in the BGP, in the brains, and considering IPv4 as a transport. But as you are also considering maybe in next month, considering IPv4 as a services, yes, in order to have everything in IPv6. Yeah.
Right, so the idea is that we don't want to leave researchers behind, and that understanding that some researchers, they may be using data acquisition that is based on embedded Windows or something that has only IPv4, and that they still need to move their data. So one example of using the DTNs would be to have the DTN closer to that data acquisition device that can only speak v4, but the DTN can speak IPv6. And so, but that's one possible scenario. But certainly, yes, we're how to put it? We're taking the position that we want to promote IPv6, and that certainly we would consider using IPv4, providing IPv4 transport as a service within IPv6.
Alejandro Martinez, also from Universidad de Guadalajara. The question is related also to IPv6 and mainly what was the reason for choosing IPv6 peering only? Was it performance driven the decision, or plain and simple lack of IPv4 space?
Well, there are several contributing factors. And so we very much want to advocate greater IPv6 adoption. And doing nothing really didn't seem an option for us. And that if it's in one way, so we're trying to move the conversation. So that if we perhaps show some leadership and say, look, we're doing these great things with IPv6, I think we will try to help people follow us, and that there are resources to help in transition from v4 to v6. And it's really, if this helps provide more motivation to do so, that's wonderful. It is, but to one of your other questions, do we see a performance difference between v4 and v6? It depends. One of the interesting things that we find that when we're doing our measurement is that on our persona dashboard, we have v4 only and v6 only grids, and the performance is not the same. And so it's often you might find that v4 and v6 are not congruent in terms of the routing. And so that you may see, just as with IPv4, you may see an asymmetry between the forward path and the reverse path. The IPv6 may follow a completely different path, both for forward and reverse. So there's not, but I would consider that a pathology that would be not necessarily inherent, that v6 is inherently faster than IPv4. It's just that organizations are in different places on their progression in terms of adoption for IPv6, because we do have to be sensitive to that, even down to the system administrative level. Our sysadmins may be comfortable with developing firewall rule sets for IPv4, but they may not yet have considered what turning on v6 what open themselves to. So in our part, I think, is to help drive adoption of IP6 and then help people both become aware and solve the challenges in transitioning from v4 to v6. But again, to one of your other questions, the address space exhaustion is out of IPv4. We're, at least in North America, we're already there. The other NICs are facing, yes, certainly. And even within California, we have institutions that have not just one depth of NAT, but maybe two depths of NAT. And that just, it's adding, we would like to remove or mitigate that complexity. So yes, driving IPv6 is among our goals. Thank you.
Thank you, John, for joining us this afternoon. And on behalf of the CUDI community will give you a certificate of appreciation for coming down here and sharing what you've done with CINIC. Thank you very much, John.